So as you can see here, I mean, last time we have been talking about this adaptive linear neuron. So, and to train this model, I mean, this model is very simple. It's similar to a perceptron, but instead of using hard limb or step activation function, we use this activation function. It's linear activation function. We can use this one for regression, and at the same time, we can use it also for classification. If you want to
Excuse
use,
me?
yeah,
I don't see your screen. Do the
cannot,
other people do?
you cannot see the screen.
No.
Okay. Uh, Maybe I'm sharing the wrong one. Yes. Can you see now?
Yeah.
Okay. So this model, it's very similar to a perceptron, but instead of using step function, we are using this linear activation function. If you will use this model, only that this one, we can use this one for regression, right? That part. So if we will get the output from here, we can use it for regression. But if you will use this threshold function, we can convert this regression problem into classification problem. So in fact, all classification problems are initially regression problems, because in feed-forward neural network, we have this block all time. We have this block. We have this summation, weighted sum of inputs. We have also, you can just say that we have linear activation function, or we don't have it. So this is common part in feed-forward neural network. So if you will use that part, we can use this one for regression. If you want to convert it to classification problem, we need to use this threshold function. And this threshold function, it's very simple. We can just say that if y is greater than or equal 0, net, for example, I can just call it net, for example. If net greater than or equal 0, y equal 1, otherwise y equal 0. So we can convert the output from that point into binary classification problem. In a perceptron, we use the perceptron learning rule, and to adjust the weights in a perceptron, we just multiply learning rate times error times input. But here, we will use a gradient descent approach, and in this gradient descent, delta omega will be minus eta multiplied by the gradient. And the gradient of, it's the first derivative of the cost function. So we need to define a cost function. So the cost function here, or objective function here, it will be, mean squared error. So we can just say that this one, it's mean squared error, for example. Maybe it's not mean squared error. So it's a summation of t minus y squared. So delta omega will be minus eta multiplied by this partial j by partial omega. Partial j by partial omega, it will be partial j by partial y times partial y by partial omega. So we call it chain rule, right? We call it chain rule, and we can just find the delta omega and train the model. So this one, we call it adaptive linear neuron, or they call it ADALine. Shortly, it's ADALine, for example. We have another one also, which is logistic regression classifier. This logistic regression classifier, it's exactly the same, but instead of using linear activation function, we use this sigmoid activation function or logistic function. We just use this one. So if you change the activation function with this one, we can call it logistic regression classifier. And it's the same also. If you want to convert this problem into classification problem, we can just use this one. So here you will get probabilities, for example, number between 0 and 1. And if you want to convert it into classification, you just need to add this step function or a hard limb function at the end. So it's exactly the same, no difference at all. No difference. And if you want to use a logistic regression, you can get it from sklearn. We have a set of linear models in sklearn. So from sklearn, we can import logistic regression. And if you want to implement it, of course, it's okay. But you can just simply use it from sklearn. You can get this logistic regression. So logistic regression classifier, it's exactly the same. So we have 3 different functions in our models. We have perceptron. The perceptron, it's binary classifier, or we are using a step activation function, right? We can have ADALine, for example, for regression problems, and instead of using, we will use linear activation function, and here we will use linear activation function. Here we will use this kind of sigmoid activation function, and it's the same way also. If you want to adjust weights, if you want to train this model, you need to use gradient descent. Just simple problem here. Net will be omega tx, for example, plus p, right? and this activation function, it's 1 divided by 1 plus exponential minus net. And you can use this hypothesis here if you want to convert this problem into classification problem. So we need to agree that all classification problems are in fact originally regression problems, because we do those regressions, we calculate those numbers, and after that we can apply this hypothesis here to convert any regression problem into classification problem. So this is we have the link for this code, in fact, this logistic regression, and you can just train it, for example, and after that you can print the coefficient and the intercept. When you print coefficients, it means it's omega values, and when you print intercept, it's the bias value. So this one, in fact, it's the bias. If you want to see what is the bias value, and those ones are omega. For example, omega 1, omega 2, omega 3, and so on. If you want to implement it, this sigmoid function, it's exponential divided by 1 plus exponentially. So you can just implement it using this one, for example. So the exponential function, or this sigmoid function, in fact, it's 1 divided by 1 plus exponential minus net. You can multiply by e plus e exponential plus net, exponential plus net. So it will be exponential plus net divided by 1 plus exponential plus net. So in the perceptron, in fact, we update weights after each individual training sample. So we can just say it's a stochastic gradient. It's similar to stochastic gradient descent. We update it example by example. We can also still calculate the gradient and update weights after each individual training. And you can also calculate the gradient and update the weights based on the whole training dataset, which is batch gradient descent. So today we have 3 models. So in fact, if you are working with maybe classification problem, maybe regression problem, you can pick one of those models and start working with it. So because I mean, those models are nice and are important to know. The training mode, we talked about the training mode last time. We have maybe 2, or we can call it 3 training modes. For example, it's a stochastic gradient descent, and in stochastic gradient descent, we call it online learning. So we train the model example by example. This is very suitable for online, because in online, you don't need to get your whole data set and after that train your model. But once you have a new example, you can retrain your model, and therefore they call it stochastic gradient descent. Sometimes we build systems and we are getting some training examples, for example. So we can just train the model at any point using stochastic gradient descent. In batch gradient descent, we calculate the gradient based on the whole data set. We have the mean gradient based on the whole data set, and we adjust the model, we adjust the weights 1 time each batch. So in a stochastic gradient descent, in fact, we adjust the weights by the number of data points, by the size of batch size. So for example, your data set, the size is n, for example. So we update the weights n times in each batch. So this one, it takes too much time. In fact, in stochastic gradient descent, maybe it's noisy. So when you see the training error and stuff like this, you can see that it's a little bit noisy. But in batch gradient, we calculate the gradient from each example, and at the end we have the mean gradient. We use this mean gradient for adjusting the weights only 1 time each epoch, right? So the problem here in batch gradient, we need maybe GPU memory, large one, because you need to have all your data points in the memory at the same time. And you need to calculate all those calculations, keep it in the memory, because I need to have the mean gradient. So I need to have all my calculations in the memory. So sometimes it's complex, because maybe you are working with videos, you are working with images, for example, high definition. So it will be impossible for your memory to have all data points at the same time. So in this case, we can go to mini batch gradient. So mini batch gradient, it's a trade-off between the 2 approaches. So we just divide the data points into a number of batches, and we treat it batch by batch, for example. So in this case, we do it only for the memory issue, right? For just the memory. So we divide data points into mini batches due to memory restrictions. How can we select the learning rate? If you select it too large, it might overshoot, right? And if it is, and it will fail to converge. Maybe it will diverge. If it is too small, for example, it will take more time for learning. So I mean, it's by trial and error. I mean, there is no approach for doing it, right? So it's just by trial and error. Maybe you can use, for example, grid search. grid search, we can just create some points. So for example, if we use this grid search for testing different hyperparameters. So for the learning rate, we can test some points, for example, and yes. So implementation, how can we implement? So it's adaptive linear unit, in fact. This one, it's adaptive linear unit. I mean, if you want to implement, I just uploaded some data points here. It's Iris, by the way, and we used also the first 100 points. So we restrict ourselves to binary classification problem, because we know that Iris dataset, we have 3 classes, but we will select the first 100 points, so we can limit ourselves to binary classification problem. So we selected the first 100 points, and we used also 2 classes. We used the 2 features, feature number 0 and feature number 0, 1, 2, 0, 1, 2, and number 3, for example. So I guess it's a beta length and Sybil length. So we have 2 features, and after that, we try to build the model. I mean, this model is very simple, very simple one. So we have X, we have T, we just, I mean, net equal X multiplied by omega plus B. So this equation here, it's omega X plus B, in fact. So net equal omega X plus B, and after that, you will apply linear activation function. Do you see? Y equal net, which means we have linear activation function. And after that, we need to calculate the error. And once you have calculating the error, you can just use the formula for adjusting the weights. So omega or delta omega equal eta multiplied by mean error, and the bias will be eta multiplied by the error. So if we can go to this equation, yes, it's this one. Do you see this equation here? So it's eta multiplied by error multiplied by input, right? So here it's eta multiplied by error multiplied by input. And I did it here, in fact, for batch gradient. So I'm just applying here batch gradient. So I'm doing it 1 time each epoch. We are doing here for each epoch. Yes. So you can just train the data points, and this is how the training error look like. And here this is the model. And last time we discussed how can we plot this decision line. So I mean this decision line, I mean the model at the end, we will have this equation. We will have, for example, y equal omega x plus b. We have 2 inputs, so it will be like, or I can just say, I mean this is the decision line, which equals 0, for example. So it's omega 1 x1 plus omega 2 x2 plus b equals 0. So if I want to draw this line, this one it's x1, this one it's x2, for example. So I just need to find a range of x for x1. So here I'm just selecting x1 equal all points in this range from x1 minimum to x1 maximum using this step, for example. And after that, I will substitute those values into this equation. So I need to get x2. So in this case, x2 will be minus omega 1 x1 minus b divided by, all this one will be divided by omega 1. So we can draw this line. So this is very simple. I mean, I will show you also another approach. We can just use a model. We can create also a grid of points. So for example, you can create a grid between x1 and x2 and substitute all these values to the model. We use predict, model.predict, for example. So it's just a comparison between learning rates. Sometimes when it's very small, it's okay. But when you increase a little bit, the model will diverge. It will diverge because maybe it's too big for the problem. Maybe it looks, I mean, it's like this one. So we will oscillate here at that point. So we need to be careful when we are selecting the learning rate. But also, I mean, if you can standardize and normalize your data points, maybe the performance will be much better. So how to improve gradient descent through feature scaling? Those features.
I'm sorry.
Yeah.
I have a question about the why? Because I checked the Google Colab before about this, and why it is diverging? I don't understand. Because if the learning rates are even they are large, it should maintain at a steady state error. It's about a steady state. Right? It's like why is it diverging? It should be resonating between 2 points.
No. Do you see this curve, for example? I mean, this curve, it's an objective function. How does objective function look like?
Yeah.
When we
So
select
it's like always. It's like
it overshoots. I mean, when we are close, when we are close to, I mean, to the bottom point here, right? Saddle point.
Yeah.
When we are close to this point here, maybe it diverge. It's because it's error. Maybe we have this. Do you know we have we have vanishing gradient and exploding gradient. Maybe you have an exploding gradient, right? So this exploding gradient means that the gradient is increasing, and in this case, we will
because every time it's moved to the opposite direction, so it should be it's like resonating between 2 points at the same curve. It's
yes. So if
cost function is
if you are starting from this point, we are moving again with the gradient. Maybe we will go like this. At some point, it is too much. It will be like this. So maybe at some point, it will be like this one. So now it's not optimum. We need to go back here. So you will keep overshooting around. Okay,
but around the point, it never converge. It never
converge.
It's a convex function, and it's always going to the opposite direction of the.
Yes.
So why it should diverge? I think.
Because the step size, maybe the step size is too big.
Okay, too big a step size. Let's assume too big.
Yes, because the step size, this one, it's the step size. We have this, I mean, this is delta omega, delta theta or delta omega, for example. So delta omega equal minus theta multiplied by partial E by partial omega. So this is the gradient. In fact, we need to check the gradient. We have something called exploding gradient. Maybe the gradient is exploding, right? So
okay, but here it's convex, so it's not a. Maybe it's have a steady state error, but it doesn't diverge.
No, because I mean, I don't know how this one look like. Is it flat or not flat? So imagine that it looks like this one, and the step size is very big step size.
Okay.
So
even with big step size, it doesn't diverge.
No. If it is big step size, you will oscillate or you will overshoot around this saddle point, and you will not be able to reach this point. So we're just coming here, and after that we go back here, we come back here, go back here, right? So we will not be able to reach this point because we know that the error here is 0, close to 0, for example. So you are decreasing, right? And at some point you start decreasing again, and you cannot reach this point. I mean, we need to be able to reach this point here. So in this case, the model will not, because to converge, in fact, we need to reach the point where partial E by partial omega equals 0, right? So if this step size is too big, you'll not be able to, maybe you are moving with this step, right? So you'll not be able to reach this point. So you'll keep oscillating around this area. You will not be able to reach this point.
Yeah, I agree with that totally.
Yes.
Yes, I have a question as well related to.
Yes.
If I remember very well, this problem of conversion is related to the choice of the loss function that we are choosing. Yeah, and concerning this loss function, which plays an important role in backpropagation and optimization, does it need to have some specificities? For example, if it is bounded between 0 and 1, or should it is it more recommended to have a loss function that doesn't have a boundary, that doesn't squash the error between 0 and 1?
Do you mean do you talk about the cost function or the activation function?
No, the cost function, the cost or the loss. Yeah, the cost.
So this function, the error equal, for example, half this one, t minus y squared. Right?
Exactly. Yes. This is not bounded, so this can be any number. It can be you can have an error of 1,000. You can have an error of 0.1. But in case we have loss function that is bounded, it means that it doesn't allow the error to be bigger than 1 or less than 0.
So we will crop it. For example, we will crop large values. But because it's based on the target values, so what are the target values? Right?
Yeah, but for example, if we take here the same function that you are looking at, and if we make t minus y over t, so it's going to be bounded. So whatever number you are going to.
So you want to normalize it?
Yeah. So what will happen to this? Is it recommended to have the error between 0 and 1, or?
No, I don't think so, because I mean the most important here it's the gradient of this function, right? This is the most important for us. So of course, if you will normalize it, we will avoid this exploding gradient, for example. So maybe the performance will be better, but we need to have an example and we need to test it. So so for example, you can, if you have a simple regression problems, you can try to normalize this cost function. I'm sure that the performance will be better, right? But
I tried it. To be honest. It wasn't the best. Sometimes it did work better. Sometimes it did not. So empirically speaking, I think it depends on the data set. But I was just asking maybe because if the theory says that you cannot do it, but from what I understood, like there is no reason to not normalize it if a person wants to try it, I guess.
So I mean, we need to test this. Yeah.
Can I add something?
Yes.
If we take a look at this function, which was it the convex, the word with local minima, how can it ever be from 0 to 1? Because it doesn't have limits. It just goes to infinity.
No, it's not to infinity. In fact, for example, if we are predicting income and income, it's in millions, for example, right? And the model will start predicting some values. So maybe at the beginning, this error should be very large value, right? The error at the beginning should be very large value, and then when the model trains the data set, this error should be very, very small, close to 0, for example. So so I don't think it's very important to be normalized or to start from to be between 0 and 1, because in this case you need to normalize your outputs, right? So for example, if I need to predict room temperature, which is maybe should be 20 degrees, for example. So in this case, I want to normalize all my target feature. So is it correct? Is it possible to normalize those values? So this is the question. I mean, do we need to normalize those values? And we need to normalize the inputs. We need to normalize the input features, not the target feature. I mean, this is why we need to normalize it. We need to normalize it because of the activation functions. Yeah. If you want to normalize also your target features, maybe it could be something, right? Maybe it will help. I mean, even if we normalized all those numbers, the performance of the gradient descent will be much better, in fact. But I don't know if it is. I mean, it's according to the problem which you are solving. Is it possible to normalize or not, for example, right? So this.
Can I add something?
Yes.
Can you go to the next slide, please?
Yes.
Maybe the one with this the error function.
This one.
And the next one. With the here.
Here.
Yeah. In this one, this is the error for batch gradient.
Maybe this one. I got this one from this problem, right? So.
Because if it is about the batch gradient, I think
yes, it's for batch. Batch gradient, in fact,
maybe we should
batch gradient, because here I calculate net for all data points for all x, and after that we calculate the error for all values, and after that we calculate we get this. So the error here will be vector. In fact, this error will be vector. This one, it's a vector. Right?
So maybe we should we need to divide it by the length of the batch.
Yes, I'm getting the mean here, right? So I'm multiplying it. I mean, so the gradient here, it will be the gradient here, as you can see here. So this one, do you see? So it's a summation of t minus y multiplied by x. So if we need to get it batch for batch, so we need to get its mean value. So I used this function here to get the mean value. So it's error times x, and I'm getting the mean value. So I'm just using this mean as a function to get the mean, right? So if you want to do it one by one, you can just multiply t by y, multiplied by hx, get the summation, and divide by the number. So you can get the mean, but I'm using this one here, right? So, but we just need to test it. I mean, how can we improve it? Is it really very sensitive to the error rate if we change it a little bit? So I didn't run this example for maybe from last semester. We need to run this example again and try to see if it is really very sensitive and how can we improve it. Maybe we need to, do you see here, I use the inputs without normalizing those inputs. So I'm sure that if you normalize inputs, the performance will be much better. Because we didn't standardize, we didn't normalize the inputs. I'm using those numbers as it is, right? So maybe if we normalize it, the performance will be better.
Thank you.
Yes. So I mean, how to improve the gradient descent? It's by feature scaling. Scaling means we can standardize. For example, standardization will shift the mean and the variance of each feature. So maybe you have those values like this. If you will try to standardize it, you will have mean value of 1 and the standard deviation of 0, right? So for example, this is one feature, right? This is one of the features. And if you can standardize it, it will have mean value at 0 and the standard deviation of 1, standard deviation of 1. So it will be like this one. So standardization is very important. Normalization also is very, very important. So this is the performance when we standardized. So when we scaled features, this is the performance of the training error. Maybe so we start from very large value, and after that, this one will go down until some point. But maybe we need to train the model more to achieve better results. So if you can see here, training error, yes. So this one, it's a very simple example. This one, very simple example. We just have a very small, we just made this data set, for example. We have a table, and this table has number of years of experience. So this one, it's number of years of experience, and this one, it's income. We made this data set, in fact. So if you are working 1 year, you will get this salary. If you are working 2 years, you will get this salary. So this is years of experience in x-axis and annual salary in y-axis. We have those data points. We generated those data points, and we need to use this model for building a prediction model for this annual income, for example. Or so we just used the same one, and at the end we got this line. So this is our model. This model, in fact, it's equation. So it's omega x plus b, or we can just say it's omega 1 x1 plus b, right? Equals 0. So this is omega value, and this is y-intercept from this model. So when we train the model, we need to get this omega value. We need to get the y-intercept. We got those values from these data points. And I'm just comparing it with a regression model. So it's almost, so yes. So any question in that part? Any question for that part before we just talk about activation functions and quickly activation functions? Say something about it. So now you have this model, this adaptive linear neuron, for example. You have logistic regression. You have this logistic regression if you want to predict probability, for example, this logistic regression, right? Logistic regression classifier, and we have perceptron. So in fact, we studied 3 models. We have perceptron. We have this logistic regression classifier. the perceptron, it's binary classifier. You can use logistic regression to predict the probability, for example, because the output from here will be a number between 0 and 1. So you can just say it's probability. If you want to convert it into classification problem, you need to use this step function. So if the output is greater than or equal 0.5, it will be 1, otherwise it will be 0. So we can convert the number from here into binary classification problems, 0s and 1s, right? So, and it's the same way also, this logistic, adaptive linear neuron also, it's the same. We can use it for regression. So using this linear activation function. So when you change the activation function, you will change the whole task. So selecting activation function is very, very important when you are selecting it in your model, which activation function. And it's maybe wise to test different activation function. So maybe if you are building a model for any kind of problems, really, you just test 3-4 different activation functions and have a nice table in your data and just compare with the performance using this one is this. So at the end, we recommend to use this kind of activation function, right? you can try different activation function. If you didn't see any difference, so it's fine. So okay, we have tested it, right? It could be one line in your results in your paper, for example, right? But if there is some difference, you can just have a table, for example, and you can select the model or the specifications of the model which give you better performance. So maybe we can quickly just to talk quickly about those activations, because those activation functions are very important. As you can see, when we change the activation function, the output will be different, and the name of the model will be different. The function of the model will be different. So there are some linear activation functions and non-linear activation functions. We can start with this hard limb function. We used this hard limb in the perceptron. So they call it hard limb or symmetric hard limb activation function, right? So it could be symmetric or so if it is, it could be like this one from 0 to 1, right? From 0 to 1, and it could be also symmetric. So we can have this kind of, so it could be from -1 to +1, for example, right? So it's according to how you will formulate your data set. So for example, in Iris data set, if we will change each, if we will represent the classes by 0 and 1, in this case, we can use this one. If you want to use symmetric step function, you can replace the classes and represent the classes by +1 and -1. So I mean, there is no big deal here. So, but this is the function, and it's used for binary classification. And the first derivative of this function will be this spike. So we cannot use here gradient descent because the differentiation will be a big problem here. It will be 0 here, 0 here, and the +infinity here. So they call it impulse function. So this function, we cannot use this function with gradient descent. So if you will use a perceptron with perceptron learning rule, in this case, we can use this function. If you want to use gradient descent, so in this case, we cannot use a step function, and we can use just this one, for example. You see sigmoid function. So instead of using a step, we can use a sigmoid. Because a sigmoid, we will have the same output, but this function, it's differentiable. We can differentiate this one. So instead of using step, we need to use sigmoid, which is exponential net divided by 1 plus exponential net. This one, it's differentiable. We can differentiate it, right? So this is the sigmoid. So the sigmoid, it's this red one. So the output will be number between 0 and 1, right? And if you can see here, this is the x-axis, and this is the y-axis. So the problem here in this activation function, it squashes all positive values into +1 and all negative values into 0, correct? Do you see the compression or squashing effect? So if you have a perceptron, and in this perceptron you are using sigmoid, so just remember that all positive values will be converted into +1 and all negative values will be converted into 0, right? So, and this is why we need to normalize, because when we normalize, we will be sure that all values will be here in this area between 0 and 1. So when it's between 0 and 1, in fact, we will have some variations here. We will keep those. We will keep all data points in that place. So imagine that we have a regression problem, and we talk about maybe income of people or room temperature, for example. So the room temperature, it's number between 0 and 20 degrees, for example. If you will use this function, all temperatures above maybe 5, from 5 to 25 will be converted into +1. Do you see the huge impact? So all temperatures between 5 and 25 will be converted into +1. So in fact, we are destroying the data set when we are using this function. You can just say that we ignore lots of variations and lots of information from my data set, because we are squashing all inputs into +1 using this kind of activation function. Just imagine we have here from 0 to 5. From 0 to 5, we will have some variations here, because those numbers will be mapped into those numbers, right? It will be mapped onto those numbers. But all positive values greater than 5 will be converted into +1, right? So in fact, we have data, we collected data, we spend the money for collecting those data, but we are destroying the data set when we are using this function, because if we didn't normalize, we are losing lots of knowledge, because all values greater than 5, for example, it will be converted into +1. So it doesn't matter, right? If it is 17.5, 25, 13.6. We don't care. All those numbers will be just converted into +1. And this is a big problem. So it's a very, very important. If you will use this kind of activation function to normalize your data points. When we normalize it, we will be sure that all values will be represented. 25 degrees, maybe it will be +1. 24 degrees, maybe it will be 0.978, for example. 20 degrees, it will be converted into 0.867, for example, right? So in this case, when we normalize data points, we will be sure that all data points are represented here. This is the function, and when we differentiate it, we will get this green one, right? So this is a problem here when we are using a gradient descent. So all values here, all values will be converted into very, very small. Do you see? It's almost 0.2, for example, or 0.25. Maybe this one it's 0.25. So this is they call it vanishing gradient effect of this function when we differentiate it. Because when we differentiate this function, I mean the maximum value will be very small value. So I mean the value of this function when we have this partial e by partial omega, it will be very small value. It will be a number between 0 and 0.25. And in feed-forward neural network, we have multi-layer. When we have multi-layer perceptron or multi-layers, we just multiply several times, and you multiply small values by small values, so it will be much smaller values. So at some point, when we are training our feed-forward neural network, this value, this gradient, will be very, very small value. It will be close to 0. And when it's close to 0, we will not be able to adjust weights, right? So do you remember, I mean, we have delta omega equal minus eta multiplied by partial e by partial omega. If this value is very, very small, it will get smaller and smaller. Because in gradient, in error backpropagation, we go from one layer to another layer until we reach the input. We adjust weights which are connected to the output first. We will go to the next layer, until we go to the input, for example. So at some point, this delta omega will be very, very small, close to 0. When this value is close to 0, we will not be able to adjust weights. And you know that we initialize the weights by random values. So if we will not be able to adjust the weights, we will keep those random values forever. And those random values will be multiplied by the input values. So the input values will be converted into random values, because random value multiplied by number, it will be random value, right? So in fact, we are destroying also our data sets when we have this kind of problem. So this problem, they call it vanishing gradient problem. Vanishing gradient problem. So this function, it has only this negative impact, in fact. So this one this function is very nice function. We can use it, for example, when we have multi-layer, which consists of 2 hidden layers, or 3 hidden layers. But if you will go deeply, so if your neural network will be deep neural network, if you have multi-layers, maybe 3, 4, 5, for example, we will have this kind of problem, vanishing gradient problem. Why is this vanishing gradient problem? Because the first derivative of this function will be a very small number, will be that part. And in error backpropagation, we keep multiplying those numbers several times, so it will be much, much smaller. So at some point, delta omega will be very, very small number, and we will not be able to adjust weights. And if you cannot adjust weights, you cannot train your model. So I mean, your computer will keep running, maybe for many hours, and there is no difference. In fact, I mean, we cannot see any change in my error, my performance. I mean, the performance, maybe it's the same, maybe it's improving a little bit, right? It's okay if we can discover it. So if we can discover that we have vanishing gradient problem, this is very good, because we can fix it. But the problem is that you can train your model, and the one input layer, for example, I mean the input layer, for example, you cannot adjust those weights. So it means, and your model is fantastic, and you feel that the response is okay, but just remember that you destroyed your data set by multiplying your inputs by random values, because your model will see random values. Because we have omega x, just remember, omega x, we have this omega x plus p. So at some point, if we cannot adjust, we initialize those omega values by random values. So it will be random value multiplied by x. So in this case, my model will see just random values. It will not see any useful data. So we need to be very careful. So this function, the problem of this function here, it's a vanishing gradient problem. Yes, do you have any question, Ali?
Can we adjust eta value in order to, because we have this our error is multiplied by eta. So
but this one, yes, but I mean this one will be constant value, for example. So constant value multiplied by a value which is close to 0. So anyway, this one will be 0, right? So delta omega equal eta multiplied by the gradient. If the gradient is close to 0, anyway, delta omega will be close to 0. It will be very, very small value, in fact. So maybe it will not make any difference for us, right? Because this one, we have this vanishing gradient problem. So this vanishing gradient problem, how can we solve it? We need to use another activation function, which has better performance when we differentiate it. So for example, ReLU, I mean, we can use ReLU, for example. So ReLU, we will have better performance when we differentiate it, because ReLU, it will be like this one. This is ReLU function. When we differentiate this function, in fact, it will be like this one, because this one it's x. So this one it's ax, for example, because this is linear function. When you differentiate this one, you will get step function, correct? So in this case, when it's a step function, we are sure that the outputs are converted into, I mean, between 0 and +1, not between 0 and 0.25. So the performance of this one will be much better than this one. So because when we differentiate this one, I mean, the first derivative will have a bigger amplitude, for example. It will be number between 0 and +1. So when we multiply number between 0 and +1 several times, I mean, it will be much better than multiplying numbers between 0 and 1 divided by 4, right?
So the main problem with vanishing gradient is because of the activation function.
Yes, because we need to differentiate this function, right? We need to calculate the gradient, and the gradient will be very, very small value. It's not only because of this one, but because of this one, and because we have multi-layer, right?
Right.
So when we have multi-layer, we need to adjust the weights here first, and after that adjust weights here, and after that adjust weights here. So we go in several layers, and we calculate the delta omega. I mean, when we drive the formula for error backpropagation, you will discover that we use here in that place we use partial e by partial omega. When we move here, it will be partial e by partial omega multiplied by the first derivative here. So we started using those numbers. So when we go here, it will be those numbers multiplied by those numbers. So it will be much, much smaller. If you can visualize it also, it will be very good. So maybe you can have an example for feed-forward the neural network, and try to plot the gradient value for each layer, for example, right?
Thank you.
Yes, we have a function called the softmax, and the softmax, it's a normalized exponential function. The softmax calculates the probability distribution of the event over n different. It's exponential x, in fact, divided by the summation of all exponentials. So it's normalized as, I mean, Ahmed, he was talking today about normalized cost function. So this one, it will be a normalized exponential function. This is the softmax. So the softmax, first you need to, okay, this is a softmax. So it's exponential divided by sum of exponentials from other, outputs. So we cannot use this one for a binary classification, because binary classification, we will have only one output. So it will be one output divided by its value again. So it doesn't make any sense, in fact. So this one, it's the exponential divided by the summation of other exponentials. So we will calculate the output here, and after that, dividing the output here by the summation of the two outputs, dividing the output here by the summation of those two exponentials. So we call it normalized exponential function. So the range, the output here will be number between 0 and 1. So for example, if you try to predict two classes, class 1 and the class 2, so maybe the output here will be 0.7. So the one here, it's a guarantee that this one will be 0.3. The summation will add to 1. So hyperbolic tangent function, this hyperbolic, it's similar to sigmoid, but it's symmetric. The output will be a number between -1 and +1. So this is hyperbolic tangent function. So the output will be number between -1 and 1. This one, the performance will be much better also, because when you differentiate it, you will get this one, right? So instead of number between 0 and 0.2, similar to the sigmoid, the hyperbolic will be much better. Do you see? Now it's much better performance. So if you have vanishing gradient problem with sigmoid, you can use a hyperbolic tangent. So just replace this one. So instead of using this function, which is sigmoid, because as you can see here for this function, this is the first derivative. It's a number between 0 and 0.25. You can just use hyperbolic. So the first derivative of the hyperbolic will be number between 0 and 1. So the performance of this function will be much better. So if you feel that you have gradient vanishing gradient problem, maybe you can replace sigmoid with a hyperbolic tangent. The performance of this one will be much better. And it's easy to find its derivative. So this is the hyperbolic tangent, and its derivative will be 1 minus tan square x. So it's easy to get its first derivative. Rectified linear unit, as I told you, ReLU, it's the most used activation function in world today, in all convolutional neural network or deep learning. And it has a range between 0 and infinity. So it's the blue one here, right? So all values are squashed between 0 and infinity. So all negative values will be converted into zeros. All positive values will stay the same, in fact, right? It will be just the same as it is. Why it's the same? Because, in fact, usually, I mean, CNN, we are working with images. And the pixel value in an image, maybe it's number between 0 and 255, correct? So we don't have any negative values. So, in fact, in CNN, especially when you are working with images, so it's important because when you select the activation function, it should be based on your data set. Do you have some negative values or not? Are you interested in keeping those negative values or not? So in the output here, I mean, in an image, for example, we have some image, we classify it, we are working in pixel at the pixel level. So the pixel value will be number between 0 and 255. So in this case, it's safe to use ReLU. This one, it will turn negative input values into zeros, and which turn, I mean, resulting graph. I mean, so negative values will be, I mean, so the first derivative of ReLU, it's a step function. But as I mean, if we need to, and the step function, it's a problem also. So maybe we can just use, we can use soft ReLU, they call it soft plus. This soft plus, it's a smooth approximation to rectifier. So it will be this green one, right? So instead of using ReLU, you can use this function, and in this case, you will have some negative values considered. So the ReLU, it will be maximum between 0 and x. So this is a simple function, ReLU, very, very easy to implement. So if you have some input here, so imagine that I have a number which is, for example, 10, for example. So the output will be maximum between 0 and 10, it will be 10. Imagine that I have an input which is minus 20. So in this case, it will be maximum between 0 and minus 20, which will be 0. So this is the function, ReLU. So ReLU, it's a very easy to implement. So it's next.
This ReLU is about is it used for regression or classification?
No, I mean, you can use it for regression, of course, no problem, because but if you will, but it will just focus on positive values. So for example, if I want to, if the output is number negative and positive, you cannot use ReLU, because ReLU will truncate all negative values, and it will keep only positive values, right? So it will be, because you see here maximum between 0 and x. So the output all time will be positive. All positive values will be mapped, and all negative values will be cancelled.
And so for classification, all the zeros are one class, and the plus positive values are another class.
Yeah. For example, if you are using ReLU, we should not use ReLU in the output layer, because in the output layer we need to classify. So maybe we can use softmax in the output layer. In other layers, we can use ReLU, right? Because if you want, you cannot use this one for classification. We can use this one for regression, for whatever, but this one, it will not help us to classify anything. So you can just build your model, which is multi-layer, and we can select this one for other layers. And for the output layer, if it is classification problem, we can use softmax, because softmax will help us to get probability. So you can just use one layer for softmax layer for just classifying things, but other layers you can just use ReLU. So don't use ReLU in the output layer. We are not using it in the output layer, but you can use it in the output layer if you are doing a regression, right? But remember, all your values should be between 0 and plus infinity. because if you try to regress positive values and the negative values, you will not get any negative values if you are using ReLU. Because as you can see it here, it's just, this is ReLU. So we will get only positive values. We will not get any negative value. Maybe you can use this soft plus. In this soft plus, we will get some negative values here, right? So some of it, part of it. But also we have another function. In fact, we have another function, which is I guess it's adaptive ReLU or something. We will check for it. It's a function like this one. We have those positive values. We have some negative part here. I don't remember. Maybe someone of you remember its name. So in this case, we can just keep some negative values. So there are lots of, those activation function. How can you select it? It's based on your problem and based on your data set. So, so this is the softmax. Softmax, it's this one. This is the softmax. This is the soft plus problem. And this is the first derivative of soft plus problem. Yes. How to implement ReLU? You have also this code. In fact, it's just ReLU. It's a symbol, as I told you. It's maximum between x and 0. So this is ReLU, right? So this one, it's just max between 0 and x. You will get this ReLU. Soft plus, this is a soft plus. It's a log or len 1 plus exponential x, right? And the first derivative of ReLU, it will be just this one, because this one it's y equal x. So when you differentiate that part, it will be +1, and this one will be 0 anyway, right? So it will be like this one. So it will be step. So the first derivative of this function, it will be a sigmoid. So this is a soft plus. So the first derivative of the soft plus will be sigmoid, right? And the sigmoid, it's all numbers. We have all numbers between 0 and +1. So the performance of this one will be much better in regarding a gradient, vanishing a gradient problem. Yes, because we need to take a break. I don't know, we will quickly take break because maybe you are tired. So this one, it's just simple. Derivative, we need to get the derivative because we are using a gradient descent. So it's very important to select an activation function which can be differentiated, right? Very important. So because it's up to you. If you want to implement a new function which does not exist, it's very important to get a function which can differentiate it because we need to get the gradient. If we cannot have the gradient, we will not be able to use gradient descent. So there are lots of functions. As I told you, we have this soft plus. We explained it. Yes, this one, it's exponential ReLU. This is the one which I told you about. And parametric rectified linear unit, parametric ReLU. So if you are interested in negative values, you need to use this parametric ReLU. And also we have this one also, it's exponential ReLU. So we have this family. You can just say it's ReLU family. So ReLU family, we have this ReLU. This is the basic standard version. But as I told you, we have a problem here. We will not be able to use all those negative values. If you want to solve this problem, you can select parametric. You can select parametric rectified linear unit. Or exponential linear ReLU, exponential linear unit. We can use this exponential linear unit. And we have the soft plus. We have the function and we have its derivative. This is very important because if we cannot differentiate it, we will not be able to use gradient descent and train our model. So it's very, very important when you are selecting a function that you can select a function which can differentiate it. Those functions, we have this linear function, for example, it's identity or linear function. We have this step function. This is logistic or soft step or sigmoid. This one, they call it sigmoid, right? And this one, it's hyperbolic tangent. This one, it's hyperbolic tangent. So there are lots of activation functions, but you need to, when you are selecting one, you need to decide, based on the data set and the problem which you try to solve. Just I put all in one graph here. So of course, we need the one which can give us good numbers. So the green one here, it's catastrophic. The green the first derivative here, because the values here are very, very small. So if we will keep multiplying several times, we will have this vanishing gradient problem from this one, maybe from this one as well. So this one is much better, which is hyperbolic tangent. This one is okay, very good, because this is RELU. Also, this one, it's okay, because this one we can get it from soft plus. So, so selecting, I mean, if you have this vanishing gradient problem, you will get anyway if you will use deep layer, I mean deep neural network, if it is deep. If you will go deep, please don't use some of those old functions. Try to use RELU, try to use soft plus, try to use exponential LU, for example, right? Or parametric RELU, for example. This one will be okay. You will get good performance. Otherwise, you will have this vanishing gradient problem.
Do we have to use the same one in every layer?
No, not at all. So for example, as I told Ali today, if you try to build a deep neural network for classification problem, I cannot use RELU in the output layer. So all other layers, it will be RELU except the output. We need to use softmax in the output, because the last one will make decision. In fact, she will say, okay, this image is a class 1, this one it's a class 2, for example. So I need to get probability. So those probabilities we will get it by using softmax in the output layer. So you can just select, it's hyperparameter. Just to try and test and check, and at the end you need to come up with the best performance as possible. So you need to test all those one. So here I'm talking about vanishing gradient problem, but we mentioned it already, those vanishing gradient problem. So this is the difference between sigmoid and hyperbolic tangent, right? So this is a sigmoid, this is the first derivative. If you will use hyperbolic tangent, we will get better performance, because this one will be a number between 0 and 1. So so in some cases, gradient will be vanishing. It will get smaller very quickly, and if we need to prevent it will prevent the weights from changing its value. In fact, because delta omega will be very small. If delta omega is very small, we will prevent our weights from changing its value. And in the worst case, this may completely stop the neural network from further training. It will stop your if we are lucky, in fact. Because if we are lucky, we will discover it. If we are not lucky, we will not discover it. Because you can have a vanishing gradient problem, and your model performance is okay, right? It will work, but remember, it will damage your data set. So maybe you will have a model which is working fine. We will have nice numbers, and we will have also confusion matrix at the end. Numbers looks okay, but remember, your model is not solving the problem as we are expecting, because now it deals with random inputs. Do you understand the difference? So if you will discover that you will have a vanishing problem, we can discover it that my model is not training. In fact, we can discover it. So the error curve is not going down to 0. So we know that we have a problem here. So we can fix it. But the most difficult problem, in fact, that everything looks fine. Everything looks fine, and I trained my model, and we have confusion matrix. We published our results, right? We got my PhD, and the model has been used in a hospital. But imagine it's used in a hospital with patients, but instead of working with the patient information, it multiplies all patient informations by random values, and it deals with random values, not real values. Why we have this case? Because as I told you, in the input layer, for example, we have here in the input layer, we have some inputs here. We have x1, x2, x3, for example. We have some weights here, and the weights here, in fact, we cannot train those weights. So those weights equal random values, random number. Because we trained other layers. Other layers are okay because they are close to the cost function. When we are close to the cost function, maybe we will not have huge impacts. So other layers are okay, but we go to this input layer here. So we have weights multiplied by input, and those weights cannot be adjusted because we have vanishing gradient. So in fact, what this layer C can see is x multiplied by random values all time. Can you see it? So this layer will see inputs multiplied by random values, which is random values. So instead of working with patient data, in fact, we are working with random numbers. But your model looks fine. So you have a patient, he has blood pressure, he has all those symptoms and those, how do you call it? Those blood pressure and I mean temperature and lots of numbers. But unfortunately, those numbers are multiplied by random values. So his temperature is maybe 37, for example. 37 multiplied by random value So the model see random values, and it make decision based on those random values. So it's very catastrophic. In fact, just imagine you have a patient and we need to decide if he has a disease or not a disease, for example, and we are dealing with random values, not with real values. Why we have those random values? Because we have vanishing gradient problem, and the weights in the input layer is random. We keep those random values which we initialized with at the beginning, because those weights cannot train because of delta omega. When we reach this point here, delta omega becomes 0. So this is very difficult. So if we are lucky, we will discover it. If we are not lucky, we will not discover it, and we will deliver a model which is not working correct, and we destroyed our data set as well. So this is very important problem. So how can we solve this problem? By selecting an activation function which has better performance when we differentiate it. Yes. I guess should we okay, maybe I did the problem here. So should we are you tired, or should we finish those few slides first? I cannot hear you, Ali. I'm just worried about you. Do you want to take some short 5 minutes break or 10 minutes? Or should we just continue finishing those few slides?
I think we could continue.
Okay. Is it okay, Irini? Should we take a break first? Okay, we take 10 minutes break. Yes, we can take 10 minutes break, and we will go to this slide and just cover other points and just take some presentations. Yes. Okay, thanks, guys.